אז אני לא בדיוק איפה היינו מבחינת מספור של נדמה לי שזה היה 4, מגנטיזיישן. אני צריכה לעבור לאנגלית, נכון? Okay, and we did this, I started this table for you with the analogy between the electric field and the magnetic field, and I started the analogy. I told you that you can continue it for yourself. So magnetization is the analogous of polarization. Okay. And the idea is that in certain cases, we're looking now at magnetic fields within materials, and as opposed to vacuum, and we saw that in certain cases a material which is not inherently magnetized can become magnetized. What does it mean? It means that it contains many small loops, magnetic dipoles. Hi. איתי. Hi Itai. Before you arrived, we said that we would make the lecture shorter today because there is such a small number.
It's happening in all the courses. It's not only this one.
No, I know. I'm also not taking it personally. I also understand it's a long semester, and in a normal semester you would have been done by now, but because the rest of the next 2 lectures are kind of using the second part I wanted to do, I will postpone it to Wednesday. Okay? Okay, so I'm basically finishing with magnetization today, and I'm reminding things that I said last time. So what does it mean that a medium becomes magnetized? It contains many small magnetic dipoles, which under the effect of a magnetic field will become a line, and there will be a net alignment in a certain direction of the magnetic dipole M, which will generate an overall magnetization. Okay, and the analogy we did is to polar and apolar medium with the electric field, which will not be inherently, will not have an intrinsic electric dipole, but either under the effect of stretching or alignment of a small polar molecule, we get a moment, a dipole moment, and we will become polarized. Okay, and we saw 2 causes, 2 possible causes. Okay, we talked about paramagnetism. Okay, and we talk about diamagnetism. Okay, and we saw that these 2 things can be interpreted within a very, very simple model of the electron rotating around the nuclei. Okay, we saw that this is due to the spin of the electron. So we thought that if we can understand this if we model the electron as a small charged sphere which rotates, and of course this is completely incoherent with the quantum model, but still it helps us get a quantitative idea. Okay, so these are small permanent dipoles. They're small, but actually we don't care that they're small. So permanent dipoles. Okay, so if there is an uneven number of electrons, these moments will tend to align with the magnetic field. Okay, and this is due to diamagnetism we saw can be interpreted as a consequence of the electrons rotating around the nucleus. Okay, and we saw that the field B actually modifies the velocity of the electron around the nucleus, and this too leads to some m. Okay, so rotation of electron around nucleus, and this leads to, so this we saw leads to m aligned with B0. Okay, I'm calling B0 the magnetic field that I'm applying to the system, and this we saw, and I kind of explained it quantitatively, but we didn't go into a rigorous demonstration, but this would lead to a magnetic dipole which is opposed to B0. Okay? Okay, so these are two possible causes, and we saw that overall the question we are asking when we talk about magnetic field within materials is similar to the question we ask with polarization. We have an external field B0 which leads to some magnetization. I will define M in a second, to some reaction of the material which is expressed, manifests itself with a magnetic term here which I will define in a second, and this in turn leads to some field B, and we saw that here we have some kind of circular problem because this magnetic field B will add to B0, and then the question is how do we get out of this circular situation. And just like in the electric case, can you remind me what we did in the electric case? We isolated the two problems, okay? And can you remind me what we did to solve this part?
Well, in the electric case, we just used the Maxwell's equation regarding the charges, but obviously that won't work here exactly. So,
but okay,
it would still be like the divergence, and then also along the surface also.
Exactly. So what we did in the electric case is we said, okay, we don't really know how to deal with the big P, okay, with the polarization, with induced things. What we know to do is to calculate fields from charge distributions, right? So we translated P, the polarization, into two terms, a surface distribution of charges and a volume distribution of charges. And we did it intuitively. We showed that intuitively it must work, and then we derived it more rigorously. And then we said, okay, if we translate P into distributions of charges, we are back into a situation that we know, and we can calculate fields from distributions, and we can use our usual arsenal of tools, the Gauss theorem, and the big integrals that link fields and potentials to charges, etc. And now we're going to do exactly the same. Okay, so the first part will be intuitive. I will try to convince you that magnetization actually can be translated into a term of a surface current and volume currents that are in volume. Okay, and we'll try to convince ourselves first intuitively, then we will derive it more rigorously. Okay, and I will define M in a similar way that I defined P as a density of dipole, of magnetic dipole, volume density of magnetic dipole. Okay, so dipole moment per unit of volume. Okay, in the rigorous demonstration I will define it more rigorously. Okay, and just like before, we are now ignoring the cause. Okay, so all of this, all the first parts, everything we mentioned last time was this. Okay? Now we're ignoring the causes, we're ignoring the initial B0 which led to the magnetization, and we're asking if I have a magnetized material, which fields will it induce in my material? Okay, what will be the induced field B that is generated from this magnetization? Okay, and this will be our way to get out of this circularity. So this is the field produced by magnetization. Okay, and this is the part that I'm looking at now. Okay, so let's start by convincing ourselves with some simple intuition that it should work, that I should be able to translate a situation where I have magnetization into surface current and volume current. Okay, 1 second. לצאת שנייה? Okay, so first, it's this intuitive part is explained in depth in the Griffiths. I don't have it here, and as usually, I recommend this part of the Griffiths. But I'm going to give just the main idea. Okay, so let's assume that we have a medium here which is magnetized. Okay, I'm taking the slice of this medium, okay? And here I have many, in the same way that I had many small dipole. You remember that what I did at the time was to look at small electric dipole, okay? So these were plus minuses, and what we said is that locally they cancel each other, and only at the surface I will have some net surface density. So here what I'm having is magnetic dipoles instead of electric dipoles, okay? And what it means is that I have loops of current here, okay? And you see that, okay, and I have here, the reason I oriented it in this direction is that my magnetization here is oriented like this. Okay, and what you see is that here, locally, the movement of the charges will compensate each other, right? And so, the only place where I will not have such compensation, if I look at the borders here, this will be as if I have a small movement of charge here on the border, okay, and here too, and here too, etc. So, although I don't have a movement of charges of free electrons across the entire borders, which I would have in the case of current in some electric wire, locally I have some movement of charges bound. This is what we call bound current, okay? Because the movement of charges is bound to the local small dipole. But overall, I will have this net movement of charge along the border, okay, which will be similar to a current in this border. Okay, you agree? So this will be similar or equivalent to a net current along the border. Okay, and I can do something similar in volume. It's slightly less intuitive because so for the volume part I will refer you to the Griffiths. Okay, this is for the surface part. Okay, for the volume, take magnetization. I will refer you to the Griffiths and I'll tell you exactly where it is. It's page 281. I'm not sure here, I know there are several editions of the Griffiths. I'm not sure this corresponds to the latest edition that you have, but it's done, okay, in the same way that the surface case is done. And the idea is that if you take in volume, if you look at several loops in volume and you force this magnetic small dipoles to vary in volume, still you will have some cancellation of the current locally, but it will not completely cancel because of the variation of the magnetic dipole, and this will generate some volume density of current. Okay, so this was the intuition, and now let's try to make some more rigorous derivation of this. Okay, so this was so this was under a title 5, which was called the field produced by a magnetic material. Okay, so this was 5.1 intuition. Okay, and 5.2, and do it on a new board. 5.2 will be a derivation of the bound current rule. our hypothesis is that we have some chunk of magnetized material, and we don't care how it became magnetized, but it has some magnetization M. Okay,
it's a cross product.
What?
Wouldn't the result be the cross product? How we find it?
I don't know. I didn't understand the question.
To find the bound currents, we just do the cross product of the magnetic dipole and the surface vector.
Right.
Is that how you do it? I'm asking. Because it just seems because unlike the electric dipole, which would be a dot product because it's pointing.
Yes, absolutely. We will have a cross product because we will write Savar, and we will have absolutely. But this will lead to a slightly different expression of the bound current, which will involve a rot and not a divergence of the polarization which we had before. Okay, so this is H for hypothesis. So M is given. Okay, my material is magnetized, and the question is, what is the produced field B? Okay, so I will remind you what we did very quickly in the electric case, but because the proof in the case of the magnetic case will just follow the exact same steps. Okay, so what we had was here a small volume around the point N. Okay, and here I had my origin O's, and I wrote that ON is R prime. Okay, and here I had point M. Okay, and NM was R prime minus R, and I call this R star. Okay, these are just notations for the formalism of the proof. Okay, and this was OM. So it can be slightly confusing that M will have M here and M is also on the magnetization, but I let you understand from the context which M I'm talking about. Okay, and what I used then in the electric case was the following. I wrote that the potential M was for one single dipole was P, small p, okay? You remember the difference between small p and the polarization? Okay, so NM cube. Okay, and then we used the definition of the big P as the density, the volume density of the amount of small dipoles. Okay, and we used P to write that Vm was equal to the integral over the volume of large P n and M 4 pi epsilon 0 and M theta. Okay, and then we used two tricks, if you remember. Two tricks. Okay, the first one was to use that's the gradient, and I'm putting a prime here because it's the gradient according to n's. Okay, of 1 over nm is equal to plus, I might have put a minus here, so it's a plus over nm cube. Okay, so this was one trick we used, and the other thing we used was just a result from vector calculus, that the divergence of a function's time a vector is given by this function times the divergence of the vector plus this vector dot the gradient of the function. Okay, and we used, so we used these two things, these two tricks to rewrite V with two terms. Okay, so this we put in here, and it allowed us to rewrite Vm as a sum of two terms. Okay, one which was a surface integral P ds over Nm, right? Plus 1 over 4 pi epsilon 0, a volume term minus div P over Nm d tau. Okay, and by writing this and identifying each of these terms, this allowed us to write that sigma, the surface density of bound charge, was P and X. Okay, and X is a small vector that goes out of the surface. Okay, and this gave us that that rho, the volume density, is equal to minus div of P. Okay, just by using the definition of surface density and volume density and linking them to the potential. Okay, so now we're going to do something very similar. Okay, we're going to so I'm going to write the potential for one dipole, the magnetic potential for one dipole, exactly like I did with the electric dipole. But like Itai said, we will have now a cross product instead of a dot product. Okay, so the potential for one dipole, I want to remind me. So it's mu Fs divided by 4 pi m, the magnetism. Okay, I'm doing the same as here. Okay, here I had for one electric dipole. So for one magnetic dipole, I have this expression. Okay. Okay, and so this is the equivalent of this, and then the equivalent of this will be to write that A m is equal to mu 0 divided by 4 pi times a volume integral. Okay, I'm summing all the small magnetic dipole over the volume, okay, of large M cross M, okay, because M tot, okay, is equal to the overall magnetization is given by this. This is defining what I mean by big M, okay? If you remember, I said that I have a small volume that is big enough to consider several magnetic dipoles, okay, but still small enough so that I can write integrals, right? You see what I mean? That when I define both the polarization and the magnetization, I'm looking at a volume that needs to be, on the one hand, small enough that I can define infinitesimal quantities, but large enough so that I have more than one dipole in it. Okay, this needs to be the case to define to define this, which is basically an average. Okay, if I define a density, I'm actually averaging over a small volume. Okay, and here I'm going to use the same trick as yeah, sorry, this sign keeps changing. It's a minus, yeah? Okay, so I'm using again this first trick, but the second trick, so one is going to be the same as in the electric case. Okay, and two, I will use a slightly different result from vector analysis. Okay, I'm going to use the fact that grad cross product of FA is equal to F grad cross product A minus A cross product grad A. Okay, and I'm going to write now the equivalent of this. Okay, so if I use these two in this expression, okay, I can write that this is mu 0 divided by 4p. I'm missing something here. I was missing part of the formula. So here it's nm d tau divided by nm cube, right? Mm-hmm. Make sure you agree. Okay, I was missing n. Okay, so this I will write it. I can divide it. Okay, I can use this. Okay, so I have, this will be my A here. I'm not going to write A here because it's becoming too confusing with this A. Okay, but I'm going to use here the grad results I had before and this part. Okay, and you can check that this will give me 1 over nm rot m d tau, okay, minus rot of m divided by nm d tau. Okay, so I did the first part of the work, which was dividing things into these two integrals. And for this part, I'm going to use yet another result, which is the following. We can show that for any vector t, rot of t d tau is equal so this is the Stokes theorem, T ds. This is sorry. This is not the Stokes theorem. This is just something that you can show. This is equal to minus t okay. third trick that I'm using here. Okay, so I'm going to use this to rewrite the second term of my integral. Okay, so I can rewrite that a m is equal, so this is my first term, to mu 0 for pi, a volume integral of rot of m divided by nm d tau, okay? And this, so t here is this thing, okay? So the minus turns into a plus here, plus a surface integral of m cross ds divided by nm, okay? And this does the work, right? Because I wanted to make appear one volume integral and one surface integral so that I can identify it with a volume current, volumetric currents and surface currents. You agree? So if I define J like as rot of m, right? And K, so this is a volumetric term and this is a surface term. How would I define the K?
Cross product ds.
So I still need the ds, right? So it will be n cross product a unit vector, you agree? Because I need the ds to make it a surface integral, right? Okay, so if I use these two definitions, I can write that a m is equal to mu 0 for pi j and d tau over nm plus mu 0 over 4 pi k and ds, here I can call it ds and n. Okay, so these two things are very important. Okay, and I highly encourage you to add this to the analogy table that we started. Okay, the surface term, the volume terms in as a function of the magnetization. Okay, and this has a strong methodological consequence, because instead of calculating the integral, just like I did in the electric case, I'm putting myself in a known situation where I have distributions of current either in volume or in surface, and I can get an integral over these distributions, and I don't have to deal about induced magnetization and induced dipoles anymore. Okay?
Can you repeat how you used the second trick? Who was F?
Yes.
Used M as A.
Mm-hmm. So
You move
here,
the terms around.
these things becomes FA, okay? So
It becomes grad of F.
So grad F, so M, this is A. I'm putting some Ershine here because it's not the same thing, okay? Okay, and this is grad of F. And as I'm writing, I keep hesitating about the sign is in this first identity. Like I wrote to myself, it has to be a plus, but I don't think it has to be a minus.
Where?
I will give you an answer about this next time. On the first one, whether grad of 1 over nm, it has to be a minus nm over nm cube. I think it has to be a minus, but I'm not sure anymore. But okay, this is the answer to, this is a different question. This is an answer to your question. So this is A, this is grad of F, and here I have a cross product. Okay, so I'm actually, so this is this, okay? And so I take this here and it works. Okay, okay, so as I said, I'm here now back into a known situation, which is not necessarily easy to deal with. Okay, we saw that it's not always easy to go from from distribution of charges to electric potential, but at least I do have an arsenal of tools to do this, whether the big integrals or the solving the Poisson or Laplace equations, all the methods that you saw, separation of variables, the image method, etc. So I have an arsenal of tools, and one of them, just like we had before the Gauss theorem, I also have an Ampere law. I will be able to write an Ampere law in magnetized materials. Okay, so let's write the Ampere law in magnetized. So 6 will be Ampere law in magnetized materials. Okay, and this of course will have very interesting methodological consequences. So J dot, the volume density of current, can be divided into two terms. Okay, J bound plus J free. And it should remind you what we did in the electric case. Okay, so this is a current which is due to the magnetization. Okay, the bound current is this current that I showed you intuitively, which appears because of the magnetization that produces a net current. Okay, so this is caused from the magnetization. Okay, and this is caused by. Okay, this is caused by what? By just if I have electric wires in my problems. Okay, if I have real currents that are not just emerging from the magnetization of the material. Okay, so if I have wires, etc. Okay, now let's try to write, and this is usually not something I can control, okay? Usually what I have a handle on in exercises is this part. The bound term is much harder to, it's much harder to say anything about the bound term, and this is why it's very good that we managed to express this as a function of the magnetization, okay? So let's try to write an Ampere law in the case of magnetized material. So you remember how we wrote the Ampere law, how we derived it? We derived it from the Maxwell equation, the Maxwell-Ampere equation, which reminds me of it. The Maxwell-Ampere. Should know the Maxwell equations by now.
It's so Ampere would be, well, equals mu 0
Right.
J.
Okay, and I'm still in the static case.
Yeah.
Okay, so I will open this. This is J total, right? So I will write this as a sum of J bound plus mu 0 J free. Okay? Now I want to get rid of this. I don't want to deal with bound current. I don't know how to deal with them. So I'm going to use this J bound, K bound. Okay, so J bound is equal to rho of M. So mu 0 rho of M. Okay, I hope you remember that we did very similar things with the polarization. Rho of M plus mu 0 J free. Okay. So J free is equal to rot, okay, of B over mu 0 minus M. Do you agree? I'm taking the rot here. You agree? Okay. And now in the same way that we defined D, you remember that we defined the D vector in the polarization case to rewrite a Gauss theorem in the case of polarized material. Now we're going to define, so define the definition H, which is equal to B over mu 0 minus M, okay? And so the Ampere law rewrites like what? Yes. It is what of H is equal to J free. Okay? So this is the general Ampere law. This is the Ampere law I'm writing in the case of, this would still be true. I'm rewriting it like this. Why? Because here what I did is that I got rid of J bound, okay? It's only with definitions. It's only because J bound is now hidden inside of H. But why is it methodologically interesting? Because I can measure M. I do have a handle on the magnetization. I don't have a good handle on J bound. I do have a good handle on J free. I can measure it with my ampermeter, okay? And so now I rewrote an Ampere law which only has terms on which I have some good handle, okay? This is why methodologically interesting, and so very often you will want to use the integral form of this, okay? The integral form, here we would use the Stokes theorem, okay? So you tell me what's the integral form?
Integral form would be the
of this, you take the line integral,
yeah, of h.
H dl, okay? And if you do, so what I did here is to take the surface integral and use the Stokes theorem, okay? So this will be equal to I free, to the intensity, and the enclosed intensity, okay? And what do I mean by enclosed? If I have, okay, if I have a pass, a given pass on which I do the integral, okay, and the current is going to, so it's the overall intensity that is going through this pass, okay, this line, okay? This going from here to here is just similar to writing the Ampere theorem in vacuum, okay? So if you don't remember, you can just remind yourself how I go from J to I, it's easy, okay? But this is very important because it's very useful. Okay, and so I will finish.
So מעיין, DL is the system?
Yes, it's just, yes,
DL is the
just
system.
a pass. Yes, this was just to illustrate what I mean by enclosed, the enclosed intensity. Because usually in exercises you will not use this form of the Ampere. You will use this form where you define a certain path and you use the wisely chosen one, okay, and you integrate this and you use a situation and symmetries where you can bring this out of the integral, etc., etc. Okay. Okay, so I will do two more things. So one thing I want to do is to complete the analogy that we mentioned, because there is a small subtlety. So H is not completely the analog of D. Okay, and I want to draw your attention on this. Because if you use the analogy in exercises to solve things, it's important to know exactly what is the analog of what. So I'm doing a small parenthesis to talk about the analogies. Okay, so if you remember in electrostatic, I had that rho tot was equal to rho bound plus rho free, okay? And so this allowed me to write, I did the same. I wrote the Maxwell-Gauss equation, okay? Epsilon 0, okay? And so this allowed me to write it like minus divergence of P plus rho free epsilon 0. Okay, and then I wrote that divergence of D is equal to rho free. Okay, this was the situation I had in electrostatic. Okay, so if I continue the table that I had before, electric, magnetic. Okay, so I had D, which was equal to epsilon 0 E plus P. Okay, and now I have that H is equal to B over mu 0 minus M. Okay, and then I wrote the Gauss, the Gauss theorem in magnetized material was writing that divergence of D is equal to rho free. Okay, and here the Ampere theorem is writing that rho of H is equal to J free. Right? And here I had the integral version of this. So this was Q enclosed free, and this is this is the useful version, I enclosed free. Okay, and the one last thing I defined, if you remember, was the susceptibility, the linear materials. So I will leave some room here because this is where the analogy is not completely working. Okay, so I will now define what we mean by linear materials in the context of magnetized materials, and then I will finish the analogy. If you remember, as I said, the free things, whether the free rho free or J free, is what we control. It's what we have a handle on, and we can measure. We can measure it. So this is why it's methodologically interesting to write it this way. But in the same way that I told you last time that you should be very careful. Okay, these are remarks. Okay, I told you at the time that rho of D is not 0, okay, as opposed to rho of E, which is 0 in the case of magnetostatics, right? I told you at the time that you should be careful because the divergence of a vector is not enough to define it. So you cannot just do the analogy, solve everything in terms of D as if it was E, okay? There is a deep difference here between D and E, which is that the rho of E is 0 and the rho of D is not, okay?
And I suppose the same holds for the divergence.
Exactly. So divergence of H is not 0, okay? Whereas rho of E is 0, whereas divergence of B is 0, okay? In fact, divergence of H is minus the divergence of M, right? Yes. Okay, so this was the remark, and now let me define linear material. Okay, so by definition, a linear material is a material for which I can write M, for which M, the magnetization, is proportional to H. Okay? And this is called the magnetic susceptibility. Okay? And why is it an interesting case? Because for linear materials, I can write, so for linear materials, I can write that B is proportional to H. Okay, let's show it with mu equal to mu 0, 1 plus K. Okay, so let's show it. I have that I know that mu 0 of H plus M is equal to B, and so mu 0 of H plus chi M H is equal to mu 0 H 1 plus chi M. Okay? This is the demo. Okay, and this is a bit different than in the electric case, because if you remember, in the electric case, I had that E was epsilon 0 chi E P, sorry, that P. Okay, so it's not quite the same. I will add this in the analogy. No? Okay, so what do I mean by a linear material? So in the electric case, it's a material for which I will have some proportionality between D and between D and P, but it will involve a proportionality between P and E. Okay, and in the magnetic case, okay, so here there is no epsilon 0. This is what I meant, that the analogy is slightly different. Okay? Okay? And this, if you want to write the exact analogous, because H is not the analogous of E, it's B the analogous, okay? So this H is 1 over mu b, where mu is equal to mu 0, 1 plus phi m. Okay? So this ends what I wanted to say about static magnetic fields within materials. Okay? And if I very quickly summarize, we talked about the cause that leads to magnetizations, and then we ignored the cause and we asked what field will be generated in a magnetized material, and we saw that the way to solve this is to define some magnetization and rewrite it in terms of distributions of current, surface distribution and volume distributions. And when I do this, I'm back in a well-known situation where I have all the arsenal of tools I already had to solve things. Okay, so this summarizes what I wanted to say. And next time we will not be in the static case anymore, and we will talk about waves both in vacuum and in materials. And this is what I wanted to start today, but I think it's better if... So the three of you will be here on Wednesday?
Yes, for sure. I hope so.
Okay, because I don't want you to be... להידפק בזה שהייתם פה היום שאני אתחיל רק ברביעי, בסדר?
זה בונוס, לא?
מה זה?
מה אמרנו שזה בונוס?
מה בונוס?
מי שמגיע היום.
מה בונוס? זה נקודות? לא.
בדרך כלל אף אחד לא מגיע לשיעור השלמות כי זה ב8 בבוקר, זה בעייתי.
כן, אני מבינה. מצד שני, אני עדיין חושבת שזה עדיף מלהעלות איזשהו הקלטה למודל.
אני מסכים, אבל אני גם מבין למה אנשים החלטים גרים רחוק.
גם אני, פשוט כל אחד צריך שיהיו גבולות. תודה אריאל. סיימתם את התואר בעצם? אחרי הקורס הזה? ועוד כמה קורסים?
לי יש עוד סמסטר קיץ.
זה ועוד כאן נשאר.
עוד פתיחה. טוב. בהצלחה.